All right, it's 8:30. Let's go and get started. Good morning, everyone. How's everyone doing today? Good, good, good. All right. So it's Thursday, week 2. So it's our last lecture of this week. So the plan for today is we're going to continue on with our lecture on second order ODEs. And so I'm hoping we can finish all the homogeneous stuff today. And then starting next week, we'll start talking about non-homogeneous. All right, so announcements. Remember, homework 1 is due tonight. Homework 1 is based on the first order ODEs, and so you should have everything you need to finish up that homework. If you have it done and you want to turn it in person, you're welcome to do that today as well. But if you turn it online, then you have a little bit more time because you have until 11:59 p.m. Okay. All right. I think that's all I have for kind of the introductory stuff. Are there any questions I can answer before we get started? All right, so let's go ahead and pick up where we left off. We're talking about second order. Or you're going to refer to it. All right. So we're kind of chalk or smack dab in the middle of our differential equation review. Okay, so we are going pretty fast, and so we did first order ODEs in about a lecture and a half, and so for second order ODEs we'll do it in about 3.5 lectures. Okay. All right. So for second order ODEs, we're looking at equations that contain a second order derivative. So the general form for our second order ODE is y double prime plus A of X, Y prime plus B of X, Y. That's kind of the most general form for a second order ODE, at least a linear one, right? So remember, we're restricting our discussion to just linear ODEs because they're significantly easier to solve. And so starting today, we're going to make an additional assumption. And so, a lot of the techniques that we use for second order ODEs rely on the fact that the coefficients here are strictly constants. Okay? So we're going to rely on that today. And so, if you kind of look back to where we started with first order ODEs, we're making a lot of assumptions up to this point. So the reason for that is that generally speaking, as you go up in order, to go from first order to second order to third order, and so on and so forth, it gets much harder to solve the ODEs. And so, in order to make them solvable, you have to keep kind of making this. Right. And so for today, I'm going to simplify this equation. And so I'm going to assume so the first assumption we're going to make is constant coefficient. So this basically means that A of X and B of X are constants. Okay, so that means they can't be any function of X. They can just be numbers. Okay. And another assumption that we'll make for today is we're going to assume that we have a homogeneous equation. And so the homogeneous assumption basically means that the right-hand side, R of X, is equal to 0. All right, and so if we make those two assumptions, then our differential equation becomes the following. We have y double prime plus a y prime plus b y is equal to. And so this is going to be the starting point for all of the problems we're going to do today. So all the examples, all of the theory that we're going to be working with this. So this is the second order linear with constant coefficients. And so if you remember from our discussion on Monday, one of the unique things about second order ODEs compared to first order is that we're going to get multiple solutions, right? In particular, we're going to get two unique linearly independent solutions. And so our first order of business today is to take this kind of simplified equation and come up with a way to obtain those two linearly independent solutions. So that's our first goal for today is how can we get solutions from these? All right. And so we're going to approach this in kind of a funny way, or at least I think of it as kind of a funny way. And so we have a second order differential equation here with constant coefficients. Okay? Right now we don't know how to solve it. We don't know how to get the solutions for this. But one thing we can do is we can say let's draw inspiration, or let's get some help from its first order equivalent. Because first order equations, I'd say we have a lot more robust methods for solving these equations. So if we look and see at a first order differential equation with constant coefficients, we look and see what its solution looks like, then we can kind of use that as inspiration for our second. Okay. So first order differential equation, constant coefficients looks like this. Okay. So A here is a constant, y prime is the highest order derivative. Okay. And this is what we can solve. All right, so the good thing about this is that we can this equation is very simple, so we can actually solve this with either integrating factor or separation of variables. So you can kind of pick your point here. And so I'll let you kind of fill in those details, but basically what we obtain is a solution that looks like this. We get y of x is equal to e to the lambda x. Okay. Or excuse me, e to the ax minus ax. Ahead of my notes. And so in other words, we get an exponential function where the exponential coefficient of the exponential has a constant coefficient. Okay. And so if our first order equation with a constant coefficient has an exponential solution, then let's see if we can obtain the same solution for a second order equation. So let's try y of x is equal to e to the lambda x, okay, where lambda here is a constant. And then what we're going to do is we're going to plug this into our second order ODE with a constant coefficient. Okay. So let me go ahead and write our second order ODE here again. So we have y double prime plus a y prime plus b y equal to 0. And so what I'm going to do is I'm going to plug this in for all of the y's here. And to do that, of course, we need their derivatives. And so y prime here, so we're going to take the derivative of our trial solution. And so the derivative of e to the lambda x is lambda e to the lambda x. And y double prime, of course, is lambda squared e to the lambda x. Okay. All right, so let's go ahead and plug those in. So first we have lambda, our y double prime. So y double prime is going to be lambda squared lambda x plus a y prime. So that's going to be a lambda to the lambda x plus by, and so b e to the lambda x equal to 0. All right, so let's factor out e to the lambda x. Okay, so e to the lambda x divided by lambda squared plus a lambda b 0. We're in luck because the right-hand side of this equation is equal to 0. And so we can divide both sides by e to the lambda x, and it's going to cancel out. And so we divide both sides by e to the lambda x, and we get lambda squared plus a lambda plus b 0. Let me go ahead and box this guy, right? All right. And so what I boxed right here is something that we're going to be calling the characteristic equation. So we're going to be using this a lot to solve our second order eliminations. And so one thing that's nice about this characteristic equation is that it's a quadratic equation. Right, and then what we know about quadratic equations is that they have two roots, right? And so we can use, if you're savvy and you're very good at factoring these quadratic equations, you can just kind of do it automatically. Or if you're me and you're dumb, then you can use the quadratic equations. So that's kind of the more better way. And so if we factor this equation, then we get something that looks like this. So lambda plus lambda 1 times lambda plus lambda 2 equal to 0. Lambda 1, lambda 2, these are the roots. Okay. And so if lambda 1, lambda 2 are the roots of our characteristic equation, then our two solutions are going to be based on those roots. We have y1 is going to be equal to e to the lambda 1 x, and y2 is equal to e to the lambda 2. Okay. Remember where we started. So we started kind of this journey by saying that our solution should be exponential functions, right? E to some lambda times x. And so if lambda 1, lambda 2, those are the roots of our characteristic equation, then those are going to form our two solutions. Okay. Right, and so now that we have our two solutions, we can of course take our linear combination, right? Remember, the one way we can obtain kind of a full solution is to take our two solutions and just add them together. Okay. And so our y of x equal to c1 e to the lambda 1 x plus c2 e to the lambda 2. All right, so kind of a funny, kind of like a half proof, I guess. It's not a full proof, but we kind of assumed, we kind of made an assumption in terms of what the solution looked like, and it just kind of happened to work out. So that's why I think this is kind of a funny way to kind of go about it, because it kind of seems like magic that we kind of picked. It kind of almost seems like magic that we picked this solution. Ended up working out. Any questions on this so far? All right. So let's get to actually solving some problems now. So now that we kind of have our method, so let's go ahead and try it out. And so the interesting thing about these kinds of problems is that you're going to have 3 different cases based on the roots of the characteristic equation. Okay. And so we're going to go over all 3 because each of those 3 kind of has a distinct form of the solution. Okay. Right. So the first case is the simplest case. And so the first case is in the case where we have 2 real roots. Lambda 1 and lambda 2 and real. And by real, I mean not imaginary. The second case is for when we have a double root. And so when lambda 1 and lambda 2 are the same, okay, so we have kind of 2 roots that are occurring at the same location. And the third case is when we have complex conjugate roots. And so this is when you have kind of you get an imaginary number, because if you think about the quadratic equation, I didn't even write down the quadratic equation. Maybe I should do that. If you think about the quadratic equation, there's that section with the square root. And so if you end up with a negative number under that square root, you get an imaginary number because you can't take a square root of a negative number. Okay. So I think I'll save that for later. And so, I don't want to kind of overload you with equations just now, but we'll go over we'll review the quadratic equation later. Okay, so let's do the first 2 cases first, because those are pretty simple. So let's do case 1. 2 real. Right, so case 1 is the simplest case. And so in this particular case, our solution literally just looks like our template above. And so you just take the exponential, you have 2 roots, they're both real numbers. And so you just take the exponential of those 2 real roots. Okay. So in this case, our solution is going to look like C1 e to lambda 1 x plus C2 e to lambda 2x. And there's nothing we need to change about this because lambda 1, lambda 2 are real numbers. Okay. And of course, if you wanted to complete the problem, you would be given initial conditions as well. And so you would use initial conditions to solve for C1 and C. All right, so let's do an example just so that you can kind of see it matches. Okay. And so let's say that we have a differential equation. So y double prime plus y prime minus 2y equal to 0. And we're given these initial conditions. So we have y of 0 and y prime of 0 is equal to minus. So we have a second order differential equation here. First thing we should notice here is that the coefficients are all constants. And so if you look at the coefficients in front of y prime and y, those are constant numbers. And so they don't depend on x. And more importantly, they don't depend on y. All right. And so in these particular cases, we can form our characteristic equation. And so to form the characteristic equation, you would basically take your differential equation, replace them with lambda. Okay, so everywhere you see a derivative of y, you replace it with lambda, and the power of lambda depends on the derivative of y. All right, and so let's go ahead and do that. So let's do kind of one term at a time. So we have the y double prime. The y double prime is going to turn into lambda squared. Right, because y double prime is a second order derivative, so then we get a lambda squared from that. Then we have a y prime, so y prime is going to turn into lambda. Now we have minus 2y, and so I think one, and I make this mistake all the time too. So it's tempting to go look at just the y term without the derivative and go minus 2 lambda. Okay. But you have to be careful. So when there's no derivative on the y, that means you don't multiply by a lambda. Okay. And so in this case, the minus 2y comes just a minus 2. All right, so that's our characteristic equation, lambda squared plus lambda minus 2. And so let's go ahead and find the roots of this characteristic equation. And so, just because we haven't used it yet, let's go ahead and use our quadratic formula. So if you need a refresher, the quadratic formula looks like the following. And so if we have a quadratic equation, that's a lambda squared plus e lambda. That lambda minus 7. Okay. And so we have a quadratic equation that looks like this. Then the roots, lambda 1, comma lambda 2 is equal to minus b plus or minus square root b squared as 4ac divided by 2. Okay. If you know the song to remember the quadratic equation, then that's great. I feel like I had a sad childhood because my math teachers never taught me the songs, but they just told me to remember the. Okay. All right, so let's go ahead and plug in for this. And so for our characteristic equation, okay. For our characteristic equation, a here is equal to 1, okay, because a is the coefficient in front of the second order polynomial term. B here is also equal to 1. And then C is minus 2. All right, so let's go ahead and plug in. So we have lambda 1 and lambda 2 is equal to minus b minus 1 plus or minus b squared 1 squared minus 4ac 4 times 1 minus 2 all divided by 2a 2 times . Okay. We'll go and simplify. So we have minus 1 plus or minus square root 1 minus negative 2 times 4, so that's a plus 8. Okay. And so underneath the radical here, we have 1 plus 8, so that's going to be 9. Divided by 2. Square root of 9 we know is 3. And so lambda 1, 2 is going to be -1 plus or minus square root of 9, which is 3, 2. Okay. So that means lambda 1 is equal to -1 plus 3, 2, lambda 2 is equal to -1 minus 3. We just kind of work through the algebra here. We have -1 plus 3 is equal to +2. 2 divided by 2 is 1. Okay, so lambda 1 here is 1. Lambda 2 is a -1 minus 3, which is a -4. Divided by 2 is -2. Lambda 2. All right, and so let's put this together. And so now let's form our homogeneous solution. So now that we know the two roots, we know our solution is going to be C1 e to the lambda 1x plus C2 e to the lambda 2x. Okay, let's go ahead and plug in for lambda 1 and lambda 2. And so lambda 1 we know is 1, so we have C1 e to the x plus C2 e to the -2. All right. Any questions on this so far? Yeah.
Does it matter which one is lambda 1, which one is lambda 2?
No, it doesn't. So yeah, so you have lambda 1 equal to -3 and lambda 2 is equal to 1. That's the point. Because when you apply the initial conditions, then everything's going to work out and you're going to get the same answer. Yeah. All right. So that's our homogeneous solution. And so if you'll notice here, it's still in terms of C1 and C2. Okay. And so to specify the values for C1, C2, we need to apply our initial conditions. Okay. And so we go back to the very beginning of the problem. Our initial conditions were y of 0 is equal to 4 and y prime of 0 is equal to -5. So let's go ahead and apply those down here. So we have y of 0 is equal to 4. Oh, first of all, notice we have two initial conditions, right? And the reason we have that is because we have two unknown constants, right? C1, C2. And so in order to solve for both constants, we need two initial conditions. Okay? And so that's going to be pretty common for secondary. All right. So our first condition here is y of 0 is equal to 4. So let's take our general solution up there and plug in x is equal to 0. And so that's C1 e to the 0 plus C2 e to the -2 times 0. Okay. In both cases, we have e to the 0, so we know e to the 0 is going to be 1. And so our first boundary condition equation is C1 plus C2 is equal to 4. We have one equation. We're not able to solve this equation just yet because this equation has two unknowns. And so in order to obtain the correct solution, or in order to attain both the values for C1 and C2, we need to bring the second initial condition into the form. And so our second initial condition says that y prime of 0 equal to 5. Okay. And so the fact that our initial condition here involves a derivative, that means we have to take a derivative of our, original solution. All right, so let's take y prime first. I'm going to take, our solution up here, okay, our general solution with C1, C2, and I'm going to take its derivative. So I'm going to do it one term at a time. And so we take the derivative of C1 e to the x. And so we take the derivative of that. C1 is just a constant, so we don't have to worry about that. And the derivative of e to the x is just e to the x, right? Exponentials are great because they are very solid. All right, and then we get to the second term. And so the derivative of the second term, which is C2 e to the minus 2x. Okay. The C2 is a constant, and so that just comes out. And so we take the derivative of e to the minus 2x. We apply a chain rule here, and so we take the derivative of the exponent, which is minus 2. Okay, so we have minus 2 times C2, and then the derivative of e to the x is just e to the x, and so we have minus 2 C2 e to the minus 2x. So that's the derivative of our solution. So let's go ahead and plug in 0 for this now. Okay, so y prime 0. We have C1 e to the 0 minus 2 C2 e to the minus 2 times 0. And so we simplify this, and so we have both the exponentials then go to 1. And so this is C1 minus 2 C2. Okay. And then according to our initial condition, y prime 0 is equal to 5, minus 5. I'm sorry. All right, and so our our two equations here that we're going to solve for C1, C2 are given by the law. All right, any questions on how we obtain these two equations here? Okay. Okay, so now let's go ahead and solve these two equations for C1, C2. And so you can do this many different ways. And so, not particular about the way that you choose. Right in the end. All right. And so I'll show you kind of how I usually approach these kinds of problems. So usually, when you're applying initial conditions, you get two algebraic equations, okay? And a lot of times you get situations like this, where you have both equations kind of have the same term. So the first equation has C1 with a coefficient of 1 in front. The second equation has a C1 with a coefficient of 1, okay? And so what this makes me want to do is that it makes me want to subtract the two equations. Okay. And what that's going to allow us to do is that it's going to allow us to eliminate C1. Okay. So I usually like to do this just because mentally it's just a little bit faster for me. But I think, traditionally the way that you would solve this is that you would solve one equation for one of the variables and then plug that into the other equation and solve it that way. That's perfectly fine. That's if that's how you prefer to do that, then I have no issues with that. It's just for me, it's just, this is usually just a little bit faster. I can kind of combine multiple steps into one. All right, and so if I subtract these two equations, the ones are going to cancel out. Okay. We have equation 1, equation 2, minus equation 2. Okay, so we have C1 minus C1, that is done. And then for the C2 terms, we have a C2 minus a minus 2 C2. Okay. And then on the right-hand side, we have 4 minus a negative. All right, so let's go ahead and simplify this. And so we have C2 minus a negative 2 C2. That's 3 C2. And on the right-hand side, we have 4 minus a negative 5. So that's going to give us 9. Okay, so C2, 9 over 3, which is all right. And so now the C2, we know C2 is equal to 3. Let's go ahead and plug this back in.
Oh,
Okay, so we're going to plug this in to solve for C1. You can plug into either equation. Either equation will give you the same answer. But for this particular problem, I think equation 1 is a little bit simpler. We have C1 plus C2 is equal to 4. Okay. And so we know that C1 is equal to 4 minus C2. We know that C2 is equal to 3. If C1 is equal to 4 minus 3. All right, so let's put this all together. So we know C1, we know C2, we know the general solution, and so let's put it all together. For final solution. X. C2. C1 times e to the x. C1 is 1, we have e to the x. Plus C2 times e to the minus 2x. So that's plus 3 e to the minus 2. All right, any questions on this? That's okay. Yeah. All right, so that was our kind of our first example doing a second order ODE. So I went a little bit slow here just so that you can kind of see all the steps. But you can see the process is a bit more involved than our first order ODE because we have to solve for 2 solutions and then we have to apply 2 initial conditions in order to find the final solution. All right, so that's the first case. So the first case is when you have 2 real roots. Let's move on to case 2. All right, so if you remember back from before, our case 2 is when we have a double root. And so in this case, lambda 1 and lambda 2 are the same. Okay. And so this means that when we have lambda squared plus a lambda plus b equal to 0, this backs into lambda plus lambda 1 omni squared. And so in this case, we only have one root. And so because we only have one root, we can technically only form one valid solution. Let's get y of x equal to C1 e to the lambda 1. So this is not good, right? And so we know that for a second order differential equation, we need 2 We need two solutions, right? Because what's going to happen is that, we may get a solution that looks like this, and you may think that it's okay. But every second order differential equation is always going to come with two initial conditions, right? So we're going to have usually an initial condition on just y and an initial condition on y prime as well. If we only have one solution, then our solution is not going to be compatible with both initial conditions. And so somehow we need to come up with another solution to this double root problem. All right, so to come up with another solution, we're going to use a trick called reduction of order. I shouldn't call it a trick. It's a legitimate method, right? It's a real math thing. Okay. So I'll say we'll use a technique. And the reason we need to use this technique is that, remember, we also have the restriction that whatever other solution that we come up with, it has to be linearly independent from our first solution. So we have to come up with another solution. It has to be linearly independent from our first one, and then we're going to add those two together. All right. So probably, when you went over this in 250B, they probably did kind of a lengthy proof to kind of show you, this reduction of order technique. Okay? And if you're curious, I do have the details of that proof in the notes. It is very lengthy. It's a page and a half of my notes, which usually equates to like 15-20 minutes of class time. And so kind of in the interest of time, I'm going to kind of skip it because the result is kind of a, for all this kind of building up that I'm doing, that it's, that this called reduction of order, it needs to be linearly independent. It ends up being kind of a disappointing result. And so, this is the official name for it. So reduction of order is the official name for this technique. But I think people call it by something a lot more simple, which is called the multiply by x trick. And so if I call this solution up here y1, the y1 is c1 times e to the lambda 1x. Okay. Or y2, okay, it's going to have the same root, and so we're going to have e to the lambda 1x. Okay. And so it's going to be the same root as our first solution. Okay. But what's going to be different is that we're just going to take our first solution and just multiply it by x. Okay. And so our y2 is literally just going to be the same as y1, just multiplied by x. Okay. So if y1 is c1 e to the lambda 1x, y2 is just c2x times e to the lambda 1x. Okay. And so it seems so simple. And so that's why, we can go through the whole proof. It would take probably most of the rest of the class time today, but it's kind of a silly, somewhat silly result. And so if we put this together, let's say our full solution. For the double root case. Is 5x 2 c1 e to the lambda 1 x plus c2x e to the lambda so you just multiply by x. And that's it. All right, any questions on this before we do an example? Okay. All right, so let's do an example really quick. I'm not going to give any initial conditions for this one. We're just going to solve for the general solution. We have y double prime plus x y prime 9 0. Okay. Right, and so the first thing, usually the first thing you're going to do when you come to a second order differential equation with constant coefficients is you're going to find the characteristic equation. Okay. Okay, so the characteristic equation for this case, remember we're replacing each order derivative of y with a lambda. Okay, so y double prime becomes lambda squared plus 6 lambda plus 9. Okay. Okay. So now that we have the characteristic equation, let's find the roots. And so lambda 1, lambda 2. Okay, I'm going to use the quadratic equation here. Minus 6 plus or minus square root 6 squared minus 4 times a times c, so 4 times 1 times 9, all divided by 2 times a, which is 1. And so let's take a look what's underneath the radical first. And so we have square root of 6 squared, which is 36, minus 4 times 1 times 9. 4 times 9 is 36. Okay. So we know this is going to be 0. And so lambda 1, lambda 2 here is minus 6 plus or minus 0, 2. Okay. So we have just minus 3. Okay. And so this example here, because the quantity under the radical there was 0, we end up with a double root. And so for a double root, we know exactly how to deal with these. And so we have y of x. First, our first solution is the c1 times e to the root times x. And our second solution is going to be the same as the first solution, but we're just going to multiply by . Question.
At the top, is the 9 supposed to have a y on it, or is it meant to just be 9?
Yes, that's supposed to be. Thank you. I was thinking ahead to the characters. All right, any other questions on this example here? Yeah. Yeah, so if you're good at factoring, you can do that too. I'm usually really bad at factoring. I mean, this one I have the solution in front of me, but I'm showing kind of the way with the quadratic equation just so that you can If you factor by just by inspection, it'll be -3. So if you factor this by inspection, you get lambda plus 3 squared, right? And so the root here would be -3. Because the thing that would make this 0 would be lambda is equal to minus. Yeah. All right, any other questions on this example here? All right. Oh, question. Yeah,
So after, if we were given an initial condition, we would just do the same thing.
exactly. Yeah. And so in this case, if you read the full problem in the notes is just to find the general solution. But if you're given initial conditions, you would solve it. Okay. All right. So let's go ahead and move on to case 3. Case 3, I think, being the most interesting. And so case 3 is when we have complex conjugate roots. Okay. All right, so complex conjugate roots are, let me go ahead and write the quadratic equation again. A quadratic equation is minus b minus square root of b squared. Okay. And so you obtain complex conjugate roots when the quantity underneath the radical is negative. And so just for the sake of simplicity, what I'm going to say is that b squared minus 4ac. I'm going to set this equal to let's see. Okay, and so just for the sake of simplicity, I'm going to say that if this is negative, then we're going to say that omega squared, we're going to define omega squared equal to e minus 1/4 a. And so if we could make this definition here, then our lambda, our solutions, our roots to our characteristic polynomial is equal to minus 1/2 a plus or minus I. Okay. So I here, this is our imaginary number. Yes. All right, so I wanted to get into this form because I wanted to get omega into the equation because it'll make our lives. But the most important part of this is that now our two roots, lambda 1 and lambda 2, have an imaginary component, a complex component. And so now our two solutions okay, now our two solutions are y1 equal to c1 e to the minus 1/2 a plus I omega times x, and y2 equal to d2 e minus 1/2 a minus I omega x. Right, so let's do what we usually do for these solutions, and let's take a linear combination of them. Okay, so we're just going to add them together. And so our y of x is c1 e the minus 1/2 ax times e to the I omega x. Okay, so I'm going to separate out the two exponentials just because it'll make our lives a bit easier. Okay? But remember, whenever you add exponents in the exponential, you can kind of multiply by those two. And then our second solution is C2 times e to the minus ax, e to the minus 1/2 ax times e to the minus I omega x. Okay. I'm going to go ahead and factor out e to the minus 1/2 ax. So our solution is e to the minus 1/2 ax by c1 e to the I omega x plus c2 e to the minus. All right. So this is technically the answer here. So this is technically, where you can technically stop here. If you were a fan of complex numbers, if you're a fan of imaginary numbers. But most people are not fans of imaginary numbers. And so, we're going to work on this a little bit more just to get into a form that's more recognizable. But, this is technically what you would. Okay. Okay, let's get this into a more recognizable form. Okay? Because the complex exponentials are not, usually something people like to see. And so to do this, we're going to utilize a special formula called Euler's formula. You might call it Euler's formula, depends on, how you pronounce Euler. And so Euler's formula is a special formula where if you have e to the I times something, then this is equal to cosine of that something, which in this case is t, plus I sine. So basically transform the complex exponential into cosines and sines, which are much easier to do. Another form for Euler's formula is if you have the minus version, so e to the minus it. It looks very similar. The only difference is that, we are going to use minus sign for that. Okay. All right, so let's use Euler's formula and let's plug into our complex exponentials of our general solution above. Okay. So we have y of x is equal to, we have e to the minus 1/2 ax. Okay. And then we have C1. We had C1 e to the I omega x, and so we're going to replace that with cosine omega x plus sine omega x plus, and then we're going to do the same thing for C2. So C2 okay, C2 we have e to the minus I omega x, and so we have C2 times cosine omega x minus sine omega. All right, let's group together some like terms, and so all the sine terms, let's group together, and all the cosine terms, let's group together. Okay. Group like terms, we have y of x equal to e to the minus 1/2 ax. Let's do the cosine terms first, and so the cosine terms will be c1 plus c2 cosine omega x. And then we're going to sine terms. So the sine terms are I C1 minus I C2. Sine omega x. Okay. Let's look at these terms right here. And so the coefficient in front of cosine is just C1 plus C2. Okay. We haven't applied any initial conditions yet. And so C1, C2 are still arbitrary. And so, we can still kind of just replace it with another constant. Okay. Okay. And so I'm going to replace that with another arbitrary constant. You can call it whatever you want, but I'm going to call it A. And then the second thing that I circled there, IC1 minus IC2, right? We know that C1, C2 are arbitrary. And so, we can kind of choose its values, by whatever we want. We have the imaginary number I. Okay. So technically speaking, I is also just a constant. It's a very weird constant, of course. It has very strange properties, but at its core, it's just a constant. Okay? It's just an imaginary constant. And so what we can do, because I is just a constant here, we can actually lump it in together with C1, C2. So we kind of take advantage of the fact that C1, C2 are still arbitrary. And then we can kind of replace this with another arbitrary. And so I'll call that B. Okay. And so you can see here that through the use of Euler's formula, we were able to take that imaginary number, take it out of the exponent, and kind of lump it in together with the arbitrary constant. So we kind of used a couple of things. We used Euler's formula, and we took advantage of the fact that we have arbitrary constants to kind of not eliminate the I, but kind of sweep it under the rug, kind of like the thing that you don't really want to deal with, right? And so if we kind of combine all these together, our general solution for the case when we have complex conjugates is e to the minus 1/2 multiplied by a cosine x plus b sine And so you have kind of the sine and cosine terms with a decaying exponent. This is a decaying. And so, for the last things that we'll do today, we'll do one more example. And then we'll look and see what the characteristics of this solution looks like. All right, any questions on how we obtain this solution here?
Yeah, sorry, could you just scroll up to when we were finding the general solution?
Sure. Here?
A little bit higher. Okay.
All right, any questions? Yeah.
It's the W. Is that just a constant?
So the W is, because our original characteristic equation was in terms of, E squared 4AC, this basically becomes the omega. So I just replace it with omega just to kind of make things a little bit. We'll do an example where you see kind of how we solve it. Okay. All right, so let's do one more example for today. And so we have the equation y double prime plus 0.4 times plus 9.045 to 0. All right, so we have some decimals here, and so this is probably something more common if you were to use this for like a mass spring damper, which is probably what we'll start talking about on Tuesday. Okay. And so first thing we're going to do is we're going to do our characteristic equation. So we have lambda squared plus 0.4 lambda plus 9.04. Okay. 0. So let's find the roots. 1, 2, equal 2. Minus b is minus 0.4. So minus b squared. Squared minus 4 times a times c all divided by 2a. So all divided by 2 times 1. Okay. Right. So let's go ahead and simplify this. And so lambda 1, lambda 2 is equal to minus 0.2. So minus. Okay, square root of 0.4 squared, so that's 0.16. Okay. Minus 4 times 1 times 9.04. And so that's 36.16. Okay. All divided by 2. And so we do the arithmetic up top, we end up with a negative 36. And so since we end up with a negative number underneath the radical, we know we're going to end up with complex conjugate roots. Okay. And so we take the square root of minus 36. First thing we're going to do is we're going to factor out the minus 1. And so we take out the square root of minus 1, we get I. Okay. I root 1. Okay. And so with that factored out, then we just take the square root of 36. Square root of 36 is just 6. Okay. All divided by 2. That means our roots, number 1, number 2, or minus 0.2, plus or minus 3. All right. So now that we have this as our roots, we can go ahead and form our general solution based on these two roots. Okay. And so our general solution here, first we're going to take the real part. And so the real part here is -2. And so our y of x is equal to e to the minus 0.2x. So this real part right here, minus 0.2, and the coefficient for the exponential term up there. And we have a times cosine. And then we take our imaginary part, which is 3. Okay. That's going to become the frequency of our sinusoid. So 3 or cosine of 3x plus b sine of 3x. That's all right. Any questions on how we obtained that solution there? All right. So last thing I want to do today is to just look and see what this solution looks like, because we have a fairly complex equation here. We have an exponential term and we have some sinusoid. So let's plot these and see what they look like. So first, I'm going to plot the decaying exponential. So we know that if we have e to the minus, basically e to the x term with a negative coefficient, and our plot looks like the following: x, y. So our decaying exponential would look like this. Whereas our cosine and sine, we know what those look like. So those look like an oscillating function. Okay. X, cosine starts at 1. This sine starts at 0. This. Okay. They're supposed to have the same magnitude. It's just I'm awful at drawing. Okay. All right. So what happens when you multiply these together? So when you multiply a decaying exponential multiplied by a sinusoid, what happens is that the decaying exponential will modulate the magnitude of the sine or cosine. And so what you're going to have is an oscillating function with a decaying magnitude. Okay. And so the plot looks like this. And so we may start with kind of a sinusoid that kind of looks like this, but then as time goes on, the oscillations tend to kind of die down. Okay, so that's generally kind of what you expect to see for these kinds of solutions. And so when you have kind of a decaying exponential and a sinusoid, then our solution should look kind of like this. Okay. So the reason I'm bringing this up is that, on Tuesday, what we're going to talk about is a very common physical system called the mass spring damper. And you're going to see our solution kind of look like this as well. And we're going to relate this to a lot of the physical properties like the mass, the stiffness, spring constant, and the damping. All right, any final questions on this before we wrap it up for the week? Okay, all right. So that's all I have for today. So I know I went a little bit late, so thank you guys for staying a bit longer. I'll stick around if you guys have any questions on that. Remember, homework 1 is due tonight, so make sure you get that in by the deadline of 11:59 p.m. Besides that, hope you guys have a good rest of your day. Hope you guys have a good weekend, and I will see you all on Tuesday. Did you receive a? Yes, so I know that on. But basically. I think on Monday. For now, you have my email address? Yeah. Okay, so go ahead and send me an email, I'll add it to the so that you can see the word. So then check those, I think those are just, I have to read out. Yeah, like doing some efforts. And, because exactly like you said. It'll give you instructions, so for the permit code, the email will have the code. And I think you put it into your my type here or my.
Right, see you, have a good next class.
It'll have instructions. For now, yeah, for now, just email me, I'll add you to the. Yeah. New people, any final questions? Jose, Lillian? Okay. All right, I'll see you guys next week.